Stack. This topic has been tutorialized here. A stack is like an array but with limited functionality. You can only push to add a new element to the top of the stack, pop to remove the element from the top, and peek at the top element without popping it off. Why would you want to do this? Well, in many algorithms you want to add objects to a temporary list at some point and then pull them off this list again at a later time. Often the order in which you add and remove these objects matters. A stack gives you a LIFO or last in first out order. The element you pushed last is the first one to come off with the next pop. A very similar data structure. The queue is FIFO or first in first out. For example, let's push a number on the stack. Stack push 10. The stack is now 10. Push the next number. Stack push 3. The stack is now 10. 3. Push one more number. Stack push 57. The stack is now 10. 3. 57. Let's pop the top number off the stack. Stack pop. This returns 57, because that was the most recent number we pushed. The stack is 10. 3. Again. Stack pop. This returns 3, and so on. If the stack is empty, popping returns nil, or in some implementations it gives an error message. Stack underflow. A stack is easy to create in Swift. It's just a wrapper around an array that just lets you push, pop, and look at the top element of the stack. Public struct stack. T. Fileprivat var array equals T. Public var is empty. Bool. Return array is empty. Public var count. Int. Return array count. Public mutating funt push. Element. T. Array append. Element. Public mutating funt pop T. Return array pop last. Public var top. T. Return array last. Notice that a push puts the new element at the end of the array, not the beginning. Inserting at the beginning of an array is expensive. An O-N operation, because it requires all existing array elements to be shifted in memory. Adding at the end is O-1. It always takes the same amount of time, regardless of the size of the array. Fun fact about stacks: each time you call a function or a method, the CPU places the return address on a stack. When the function ends, the CPU uses that return address to jump back to the caller. That's why if you call too many functions, for example in a recursive function that never ends, you get a so-called stack overflow as the CPU stack has run out of space. Written for Swift Algorithm Club by Matthijs Halmans. Queue. This topic has been tutorialized here. A queue is a list where you can only insert new items at the back and remove items from the front. This ensures that the first item you enqueue is also the first item you dequeue. First come, first serve. Why would you need this? Well, in many algorithms you want to add objects to a temporary list and pull them off this list later. Often the order in which you add and remove these objects matters. A queue gives you a FIFO or first in, first out order. The element you inserted first is the first one to come out. It is only fair. A similar data structure. The stack is LIFO or last in first out. Here is an example to enqueue a number.
Que en que, 10.
The queue is now 10. Add the next number to the queue.
Que en que, 3.
The queue is now 10. 3. Add one more number.
Que en que, 57.
The queue is now 10. 3. 57. Let's dequeue to pull the first element off the front of the queue.
Que de que.
This returns 10 because that was the first number we inserted. The queue is now 3. 57. Everyone moved up by one place.
Que de que.
This returns 3. The next dequeue returns 57, and so on. If the queue is empty, dequeuing returns nil, or in some implementations it gives an error message. Note: a queue is not always the best choice. If the order in which the items are added and removed from the list is not important, you can use a stack instead of a queue. Stacks are simpler and faster. The code here is a simplistic implementation of a queue in Swift. It is a wrapper around an array to enqueue, dequeue, and peek at the frontmost item. Public struct queue. T. Fileprivat var array equals T. Public var is empty. Bool. Return array is empty. Public var count. Int. Return array count. Public mutating func enqueue. Element. T. Array append. Element. Public mutating func dequeue. Comma T. If is empty.
Return nil.
Else. Return array remove first. Public var front. T. Return array first. This queue works well, but it is not optimal. Enqueuing is an O1 operation because adding to the end of an array always takes the same amount of time regardless of the size of the array. You might be wondering why appending items to an array is O1 or a constant time operation. That is because an array in Swift always has some empty space at the end. If we do the following.
var que égale à que, string,
Queue, add.
que en que, Steve,
Queue, Timmy.
Then the array might actually look like this. Ada, Steve, Tim, XXX, 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 where XXX is memory that is reserved but not filled in yet. Adding a new element to the array overwrites the next unused spot. Ada, Steve, Tim, Grace, XXX, XXX. This results by copying memory from one place to another, which is a constant time operation. There are only a limited number of unused spots at the end of the array. When the last XXX gets used, and you want to add another item, the array needs to resize to make more room. Resizing includes allocating new memory and copying all the existing data over to the new array. This is an O(n) process which is relatively slow. Since it happens occasionally, the time for appending a new element to the end of the array is still O(1) on average or O(1) amortized. The story for dequeuing is different. To dequeue, we remove the element from the beginning of the array. This is always an O(n) operation because it requires all remaining array elements to be shifted in memory. In our example, dequeuing the first element Ada copies Steve in the place of Ada, Tim in the place of Steve, and Grace in the place of Tim. Before Ada, Steve, Tim, Grace, XXX, XXX. After, Steve, Tim, Grace, XXX, XXX, XXX. Moving all these elements in memory is always an O(n) operation. So with our simple implementation of a queue, enqueuing is efficient, but dequeuing leaves something to be desired. A more efficient queue to make dequeuing efficient. We can also reserve some extra free space, but this time at the front of the array. We must write this code ourselves because the built-in Swift array does not support it. The main idea is whenever we dequeue an item, we do not shift the contents of the array to the front. Slow, but mark the item's position in the array as empty. Fast. After dequeuing Ada, the array is XXX, Steve, Tim, Grace, XXX, XXX. After dequeuing Steve, the array is left square bracket
XXX, XXX, Tim, Grace, XXX, XXX.
Because these empty spots at the front never get reused, you can periodically trim the array by moving the remaining elements to the front.
Tim, Grace, XXX, 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 XXX.
This trimming procedure involves shifting memory, which is an O(n) operation. Because this only happens once in a while, dequeuing is O(1) on average. Here is how you can implement this version of queue. Public struct queue. T. Fileprivat var array equals. T. Fileprivat var head equals 0. Public var is empty. Bool. Return count equals 0. Public var count. Int. Return array count. Head. Public mutating func enqueue. Element. T. Array append. Element. Public mutating func dequeue. Comma T. Guard head. Array count. Let element equals array. Head. Else. Return nil. Array. Head. Equals nil head plus equals 1. Let percentage equals double. Head. Double. Array count. If array count. 50 and n percentage. 0.25. Array remove first. Head. Head equals 0. Return element. Public var front. T. If is empty.
Return nil.
Else. Return array. Head. The array now stores objects of type T instead of just T because we need to mark array elements as being empty. The head variable is the index in the array of the frontmost object. Most of the new functionality sits in dequeue. When we dequeue an item, we first set array head to nil to remove the object from the array. Then, we increment head because the next item has become the front one. We go from this, Ada, Steve, Tim, Grace, XXX, XXX, head to this, XXX, Steve, Tim, Grace, XXX, XXX. Head. It is like if in a supermarket the people in the checkout lane do not shuffle forward towards the cash register, but the cash register moves up the queue. If we never remove those empty spots at the front, then the array will keep growing as we enqueue and dequeue elements. To periodically trim down the array, we do the following. Let percentage equals double, head, double, array count. If array count, 50 and percentage, 0.25, array remove first, head equals 0. This calculates the percentage of empty spots at the beginning as a ratio of the total array size. If more than 25% of the array is unused, we chop off that wasted space. However, if the array is small, we do not resize it all the time, so there must be at least 50 elements in the array before we try to trim it. Note, I just pulled these numbers out of thin air. You may need to tweak them based on the behavior of your app in a production environment. To test this in a playground, do the following.
Var Q er lik Q er, string.
Q array, empty array.
Q enqueue, add.
Q enqueue, Steve.
Q enqueue, Jimmy.
Q array, some Ada, some Steve, some Tim. Q count 3.
Q enqueue, add.
Q array, nil, some Steve, some Tim. Q count 2. Q dequeue, Steve. Q array, nil, some Tim. Q count 1. Q enqueue, Grace. Q array, nil, some Tim, some Grace. Q count 2. To test the trimming behavior, replace the line, if array count, 50 and percentage, 0.25, with, if head, 2. Now if you dequeue another object, the array will look as follows. Q dequeue, Tim. Q array, some Grace. Q count 1. The nil objects at the front have been removed, and the array is no longer wasting space. This new version of Q is not more complicated than the first one, but dequeuing is now also an O1 operation, just because we were aware about how we used the array. See also, there are many ways to create a queue. Alternative implementations use a linked list, a circular buffer, or a heap. Variations on this theme are DEQ, a double-ended queue where you can enqueue and dequeue at both ends, and priority queue, a sorted queue where the most important item is always at the front.